In this last part of the 7-part series, we're going to look at how electronics play a role in the basic automatic transmission. Modern transmissions today integrate a lot of electronic control. We have a variety of different inputs that provide information to a computer, a powertrain control module, a transmission control module. The different inputs that might affect transmission operation are going to be things like a range sensor that's going to provide information on what gear I've selected, speed sensors, things like input shaft speed, output shaft speed, crankshaft speed. There's going to be things like pressure switches or pressure sensors that are going to inform the computer when I'm in a particular gear or how much overall pressure I have. We also have inputs that provide information on load, like a mass airflow sensor or a MAP sensor. The brake switch is also an input. The computer's going to want to know that for transmission operation. Let's take a look at range sensors here for a second. I've got listed here two different types of range sensors, pressure switches and then switched ground circuits. The pressure switch type range sensor is not very common. The only reason why I mention it is because the 4L60E uses it. I'll show that in a little video coming up. But that's probably the most common transmission in the world, or at least in the US. So I figured it's definitely worth mentioning. And so this over here is basically the pressure switch type setup. And you can see they've got these different switches, and we're going to look at this. If you decide to go through a 4L60E, you'll see more of this, but there's those 5 switches, and they're controlling these 3 signal circuits here, A, B, and C. And what they do is they provide 12 volts through a PCM, and then this is a resistor right there. I don't remember what the resistance is, but let's just pretend that that's 10,000 ohms, each one of them. And they've got a little, where that arrow is, they got a little voltmeter there. They're going to read voltage. And when these switches are closed, like that one would close in low range, that one would close in reverse, it's going to end up dropping all 12 volts across that resistor. That's kind of the gist of it. So they can monitor the voltages on these 3 circuits, right where those little arrows are. They can monitor those voltages and determine whether or not these manual valve positions have been selected. So on that type of a transmission, as you go through the different gear ranges and the manual valve moves, it's going to present pressure at these different switches and open and close those switches. Now most of them are going to work like this. This is a 6L80. That's the logic for the 6L80, and then this is what the range sensor looks like. And you can see they've got A, B, C, and P. So those 4 circuits right here have switches. And when you physically shift into those different gears, in the ranges you can see here, like for example, park, it shows A is low, B is high, C is high, and P is low. So the voltage values that you're going to see right here, either going to be high or low. Once again, I got 12 volts coming in through dropping resistor. So that's a little resistor. There's 4 of them there. And they're going to monitor the voltage right where those arrows are. And if the voltage drops low, they know that the switch is closed and there's a path to ground. And then if the switch is open, like in this example for park, B and C should be open, that those 2 switches should remain open, and the voltmeters there would read 12 volts because there's no path to ground and won't drop any voltage across those resistors. Whereas P would be closed, and then that voltage would drop across this resistor and it would measure 0 volts. So those are different types of range sensors, kind of common. 6L80, pretty common transmission. It replaced the 4L60. So those are 2 examples of range sensors. This is another slide on the 6L80's internal mode switch, which is basically their range sensor. You can see this up here. I recorded a video of me operating that scan data. And you can see that's the state, the values of those 4 switches, A, B, C, and P. You can see they'll say low, high, lows. That's park, as we looked at that on the previous slide. And they go ahead and they interpret that for you, so that way you don't have to memorize that, and they'll tell you whether you're operating in park or drive, reverse, and so forth. So on the 6L80, to interpret the different ranges, you can see I've got my internal mode switch, and I've got my 4 circuits, A, B, C, and P. And you can see their states are changing because I'm going through and I'm shifting it to various manual valve positions. And as they change, the computer goes ahead and indicates whatever the relationship is between those 4 switches and whether you got park, reverse, neutral, drive, and so forth. So it's something that you could do real quick and easy if you're curious, if you've got an invalid range. Just funny I said that. As soon as I said invalid, it showed up as invalid as I skipped through it. But like if for some reason, if you aren't getting all your gears, it's always a good idea to start and look at the range sensor to make sure that it is reporting accurately. Like where there, everything's reading low, 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 and low, and that's going to be an indication of a specific manual gear. Now, this isn't indicating that, it's still saying drive, but it would be, you could refer to that chart that we had on that previous slide, and you can figure out exactly what, if that's agreeing with the manual valve position that you've selected. So it's a diagnostic step. It's something that you can do with the scan tool. This right here is the 4L60E manual valve position switch. It's what I showed a couple slides ago, just gave you an example. If you remember, this is the type that uses hydraulic pressure. The hydraulic pressure is actually going to toggle these switches. And if you look at the switches, they're kind of identifying when they're going to receive pressure. So for example, none of these receive pressure in park, and because park isn't listed as a switch. So basically the normal state that we see here is what park and neutral is going to be. So I have 12 volts on the top of each of these circuits here, and they're monitoring the voltage where those arrows are, as I mentioned before. So you can imagine right now in park, this range A is going to read 12 volts because there's no path to ground. I'll put that there, 12 volts, no path to ground. Range B does see a path to ground through switch D3 and D2, so you'll actually have 0 volts on it. And then range C does not have a path to ground, D4 is open. So that's just an example right there. It'll know you're in park or neutral just because of those 3 switch states. And then as you can go through, and like I said, if you cover if you actually work on the 4L60E, you'll be able to see more on this, but I'm just trying to give you a brief introduction to these range switches and so forth. I'm going to try something I've never tried before when teaching electronics. I'm going to kind of take everything that we talk about, inputs and outputs in the computer, and I'm going to try to demonstrate that. Pretend that this center section right here is the PCM. So we'll pretend that's a computer, we'll label it PCM. And this right here, this circuit in the middle is a breadboard. Some of you guys might have used this before if you tinker with electronics here and there. And it basically allows me to make connections and plug things in really easy. I've got, coming here on these 2 wires, I've got power from a battery pack. So I got 12 volts coming in where that red line is, and then ground where that blue line is. So everything along these rows up here is 12 volts and ground. Over here I've got a 5-volt regulator, and this 5-volt regulator is going to basically take, I got power coming into it and ground, and then the output, it outputs to this side, to the red line that we have on this side, it outputs 5 volts. And then the blue line on this side is ground. And like I said, I tied the 2 grounds together. So ground is ground, 5 volts on this line, 12 volts on that side. And over here I've got some transistors. They're actually MOSFET switches. I didn't have any transistors, so I put some N-type MOSFETs in there. I don't know a lot about the old transistors, but they will operate solenoids, so I'm going to use this side to pretty much demonstrate outputs. And everything on this side of the board, I'm going to say are inputs. And everything on this side is going to be outputs. I'll make that plural, outputs. And I'm going to wire these things up in front of you, and we're going to pretend that we're making our own little computer. Now obviously there won't be any logic involved, there won't be any processor, but we're going to deal with the hardware side of things, and hopefully it'll make a little bit of sense. All right, so first we're going to start out. One of the first things we talked about was a range sensor, and it's an earlier model. They actually got rid of these on the later model 4L60s. This is pretty common. It's probably off the most common transmission in the world, but there's a couple things in this range switch. We've got 3 channels, A, B, and C, and then on this side where you can see these wires that are twisted, that is a temp sensor, so we'll look at that afterward. But this is going to be an input. Just kind of get into this right off the bat. Your computer is going to look at all the input devices, things like switches and sensors, and it's going to make a decision based off of that information. And then it's going to control the outputs based off of that. So it's kind of like in a normal computer where you got a keyboard and a mouse. Those are inputs. And then the computer interprets what you're wanting to do and then it controls the screen or a printer or does some calculation for you, and that's an output. There's no difference really in a transmission operation. So we're going to start here with this range sensor. This is a pressure switch assembly, and what it does is it provides information to the computer. In this example, it provides information on what manual valve position I'm in. If I'm in park, neutral, reverse, drive, all that stuff. And it does so by when I'm physically moving that manual valve over, I'm exposing pressure to different ports. That opens and closes those switches. So if I were to think this generically, let me draw this up real quick. The way this works, and I've got this set up at 5 volts, but in reality it's going to use 12 volts. If I've got 5 volts, there's a resistor that it goes through, and then it goes to the switch, and then it goes to ground. That's basically how it works. When there's pressure present, it's going to close the switch, and I'm going to pass current. When there is no pressure, it's going to have that switch open. So what the computer is going to do, it's going to have a little voltmeter. It's going to monitor the voltage on the other side of this resistor. The reason why they do that is because when the circuit is open, I'm going to have 5 volts all the way up to the point of the open. So that means as long as that's open, if the switch is open, I'll have 5 volts at this voltmeter here. Now let's say the switch closes. I've got to pat the ground now, so the resistor is going to drop all the voltage. It's going to go from 5 to 0, so closed equals 0 volts. And it's all done through that switch. So the switch provides a ground, and we drop that voltage across that transistor. So we can go ahead and wire this up, and we'll see if we can make it happen. Right here, there's a tiny little resistor. I don't remember, I think I put a 10,000 ohm resistor in there. But, so that's going to mimic this resistor right there. And I've got, so on this, on these breadboards, they connect these rows together. And so if I go between ground and that row, so what I've done, get in there, okay. I've got 5 volts coming through this resistor, going to the switch, and then it will find its way to ground. And I'm going to go ahead and hook it on the other side of the resistor. I'm going to pretend that this scope is pretending to be the computer. And you can see right off the bat that the scope is showing 5 volts. It says channel overage because I'm on a 5 volt scale and it's just kissing that 5 volt mark. So I guess noise and so forth is making it go over voltage. But you can see the blue line cruising there at 5 volts. Now if I find whichever switch it is that grounds the circuit out, oh, right there. If I imagine pressure pushes down, now the voltage drops to 0. And you can see I can make it go up and down just by pushing on that switch. Now you can imagine how the computer can figure out when you're in a certain manual valve position, because it's going to see it go either high voltage or low voltage. And once it sees low voltage, it knows there's pressure there, and it knows that switch closed. Let's take a look at the temp sensors. These electronically controlled transmissions are going to have temp sensors to basically indicate what the transmission fluid temp is, but this information really carries over to things like the intake air temp sensor and the coolant temp sensor. There's really no difference. NTC means negative temperature coefficient. That means when the temperature increases, the resistance actually decreases. So the computer is going to monitor a voltage in between the TCM and that resistor. So there's our variable resistor right there, our thermistor, and this is a fixed resistor. You can see where that arrow is. They're going to monitor the voltage right there. So we're going to put 5 volts through this fixed resistor, look at the voltage on the other side of the resistor, because we're going to be sharing the voltage across these two resistors. If they're the same value, let's say they're both 10,000 ohms, then there'd be 2.5 volts left on that line. But as this one starts lowering resistance, as temperature increases, more voltage is going to drop in this first one, leaving less voltage left over on that line. So as the temperature increases, the voltage will actually decrease. That's pretty typical on how they operate. The computer is going to be able to look at the voltage values and compare that to a table that's programmed into the computer to figure out what the temperature is, whether it's coolant temp, intake air temp, or transmission fluid temp. And this shows the picture on the side here of a few different temp sensors going on. We got engine coolant temp, transmission fluid, and then the TCM. The TCM lives on this example. This is the 6L80. All these little data streams that I've got up here are just snippets from a 6L80 off of a 2014 Silverado that we've got at school. One of the things that the temp sensor is going to do is it's going to have influence over the torque converter clutch operation and also the shift characteristics of the transmission. When the engine's cold or the transmission's cold, it might delay shifts to get heat built up a little quicker, and they won't turn the torque converter clutch on until you get to a certain temperature. Basically, they let the torque converter clutch, if you remember, it's a source of heat there, right? So by keeping that torque converter clutch disengaged, you can actually increase the transmission fluid temperature quicker. So that's the reason why they use the temp sensors, for that type of information. And obviously to protect it if it gets into an overheat situation. Now this right here is my temp sensor, and I've got a thermistor built into this same pressure switch assembly. So right there, that's the thermistor. That changes resistance as temperature changes. As temperature goes up, resistance goes down. So when we heat this up, when transmission fluid heats that up, the voltage will actually drop in the circuit. So temp sensor is going to operate in the same fashion. I've got my 5 volts, and I've got a internal resistor, and then it's going to travel over to my thermistor, which changes temperature. So they'll draw an arrow through that, basically showing that that changes as temperature changes. And they're still going to look at the voltage on this side right here. This is a fixed resistor, and I got a 10,000 ohm resistor in there. And that's fixed, that stays the same. So that's basically what we're going to be doing, is we're going to be sharing the voltage drop. It's a series circuit, and this is always 10,000 ohms, and this is going to vary. It might be 20,000 ohms to start, and then the warmer it gets, it might drop down to 1,000 ohms. So the voltage will change on the wire between these two resistors, because a certain amount of voltage is going to drop in the first resistor, and a certain amount is going to drop for the second resistor. The resistor that's the highest is going to obviously take the more voltage. So when this resistance drops on the thermistor as the fluid temperature increases, more voltage will drop across the first resistor, which will leave less voltage on this wire. So let's wire this up and see how that works. All right, so now that we see that if we wire this thermistor up in line with this fixed resistor, and we got a voltmeter checking behind this fixed resistor, let's go ahead and do this experiment. I'm going to take my thermistor, I'm going to hook it up to the circuit here. So I've got this is the fixed resistor. I got 5 volts going into this fixed resistor, and then it's going to come out, and then I'm going to go into my thermistor and bring the thermistor to ground. So I'm wired just like I am here. 5 volts going through a fixed resistor and going to the thermistor to ground. I'm going to hook my scope up to the in between the two resistors, and if you look at what we have about 3.5 volts. Now I'm going to take a heat gun and we'll heat this up and we'll see how the voltage changes. I changed my scope to 500 milliseconds per division so we could see things a little across a longer period of time. So as soon as I put this heat on there, you can see the voltage drop. Take it off, climbs back up. Come back down. So you probably noticed that when I put the heat gun on there, it changed the voltage. The voltage dropped. So in the computer, they could just look at the voltage, and through a table, they can figure out what the temperature of the fluid is, or coolant, or air temperature, or anything they want to take a temperature of. So the thermistor is built into this pressure switch assembly, and as I mentioned before, they're going to have 5 volts through a fixed resistor. They're going to monitor the voltage after that fixed resistor, and as this variable resistance changes based on temperature, so is the voltage, and they're going to translate that to an actual temperature. So there's a few different types of speed sensors that we see in automobiles. More commonly in transmissions, we deal with basically 2 different types of speed sensors. One of them is this variable reluctance type. It's a 2-wire sensor, and it generates its own AC voltage. And that's what this scope pattern is down here. That shows a variable reluctance sensor. And the other type is a Hall effect. And a Hall effect is a 3-wire sensor, and it's either going to toggle a voltage to ground that's provided by the computer, like a PCM or TCM, or it's going to provide a toggling voltage to the PCM or TCM. So you'll end up seeing like a square wave pattern like we see here. Usually the voltage could be anywhere from 4 volts, 7 volts, 8 volts, 10 volts. I know this picture here shows one at 13 volts. That's probably not a speed sensor. It's just a square wave pattern I borrowed from somewhere. But another sensor is magnetoresistive. And that is more commonly found on like stability control, wheel speed sensors. But some transmissions I believe do use them. And it's a 2-wire sensor. And what they do is they provide power to the sensor, and then the sensor has an additional power supply, and it toggles that power supply on and off, and it creates a small millivolt change. So if you're looking at a 2-wire sensor and you're trying to measure resistance across and so forth, because a lot of times these things will have, I don't know, about 1,000 to maybe 2,000 ohms of resistance. That's one of the ways people check them, is just a resistance check. But a 2-wire magnetoresistive sensor, you're going to get mega ohms. It's going to be extremely high resistance. So you might think it's bad, but it actually might be a magnetoresistive sensor, and you're not going to get a lower ohmage reading like you would on a variable reluctance sensor. On this image right here, I've got a Hall effect type speed sensor. This is on a JATCO CVT transmission as an example, using an all data wiring schematic here. And you can see I've got my secondary speed sensor and my primary speed sensor. So we've got 2 pulleys in those transmissions. And the primary is the input pulley and the secondary is the output pulley. They need to know how fast those are going. So you can see they're just simple 3-wire Hall effect sensors. They got a ground, a power, and then a signal wire. And then on the primary, we got power, ground, and signal. And on that signal wire is where we're going to see that digital square wave. And the computer just basically counts 1, 2, 3. It can count how frequent those pulses are happening to figure out how fast something's spinning. This is a variable reluctance type. It's the 2-wire speed sensor. You can see they got 2 wires going in each of these speed sensors here. And basically it's the simplest type. It's the cheapest type. You basically have a coil of wire wrapped around a magnet, and then as the tone wheel is rotating next to that magnet, it's influencing the flux lines around this in the sensor around this permanent magnet. And you're causing the flux lines to collapse and expand, collapse and expand, collapse and expand. And every time it does that, every time those flux lines cut across a conductor, these little wires that we've got inside these speed sensors, it's going to induce an AC voltage. And that's what it looks like over here. You can see on the scope image that we've got, this is that positive, negative, positive, negative, positive, negative, and so forth. That's from the flux lines expanding and contracting right over those conductors. So we don't need power to these things. They generate their own power. One of the big things though with a 2-wire sensor or variable reluctance is that we need to have speed. It can't measure a shaft or a tone wheel that's spinning very slowly, because we need those, in order to induce a voltage, we need those flux lines that cut across those conductors fairly quick. If they're slowly expanding and contracting, we're not going to get a strong AC signal off of it, and then therefore you're going to end up getting a poor signal or no signal. So that's the reason why you might find a magnetoresistive or a Hall effect type sensor in place of a variable reluctance, if they have to be able to monitor a shaft spinning fairly slow. But once these things get spinning at a certain speed, their output is usually strong. And same thing with the Hall sensor. Basically, they can count the pulses, and as they count the pulses, they can figure out how fast this shaft is spinning, because they know how many teeth are on the tone wheel. So if there's 10 teeth on the tone wheel, once they see 10 pulses, they know that this shaft spun 1 turn. On this slide, I'm just showing the different RPM values that you got available. This is on the 6L80, and they've got engine speed, input shaft speed, output shaft speed. Right off of the output shaft speed, they can figure out vehicle speed, and there is an actual PID for that. I didn't include it in this. This is showing RPM, but the vehicle speed sensor PID would calculate the RPM and convert it to miles per hour. These are some calculations that the TCM can do. Is it's saying TCC slip speed. Basically, that's the difference between the engine speed and the input shaft speed, because what lives between the engine and the input shaft? The torque converter. So if they're applying the torque converter clutch, it's trying to make those two go the same speed. So like right here, you could see the difference between these two is only 4 RPM, It's serial data, it probably missed it a little bit, and it says 5 RPM there. But basically, this slip speed is always going to be whatever the difference between these two values are. Next, let's take a look at some of these speed sensors. There's two common speed sensors that we find in automatic transmissions. One of them is going to be a variable reluctance type. And a variable reluctance type is going to have just two wires going to it, nothing fancy. It's a coil of wire wrapped around a permanent magnet, and then when a tooth wheel, a reluctor ring or tone ring, whatever you want to call it, as it passes the tip of this, it takes those magnetic flux lines that are from this permanent magnet that's in there. When the tone wheel rotates and there's a gap between the permanent magnet, the flux lines can grow back out. Either when the tooth lines up, flux lines collapse, in between, grow out, so you get this constant in and out, in and out, in and out action that's going on with these flux lines. And what that does, every time a flux line collapses and expands, it's going to cut across these conductors that are inside here, that coil of wire that's wrapped around it, and it's going to induce AC voltage. So these two-wire variable reluctance type sensors don't need anything except for the wires and actual tone wheel rotating in front of it. It will generate its own signal. To make this work, I've rigged up I actually took a Honda pump gear, put it in a cordless drill here, and that way we can kind of just put the speed sensor up next to it and have this pretend like it's the tone wheel. So I got that scope hooked up to a 1-volt scale. It'll probably read a little bit better now. A little better resolution. Or I'm going to take this sensor and hold it up to this tone wheel. And you can see the frequency change, faster it goes. This toothed wheel is going to simulate a tone ring. Basically, when these teeth line up against that magnet, it's going to compress the flux lines in the magnet. And then when the opening is exposed, they're going to expand back out. And then when the tooth comes, they're going to collapse. And this constant expansion, collapse, expansion, collapse. When those flux lines cut across the conductors that are in here, they induce AC voltage. We could see that on the scope here. Actually, you can see the result of an air gap too. When I'm farther away, it doesn't really show up. The closer I get, you can see when I hit it, it's definitely doing some signal there. So what a computer is going to do, it's going to count in a period of time how often those signals switch. And based off of that, they can figure out how fast something is spinning. So if you imagine every time a voltage goes above, let's say, 1/2 of a volt, they're going to count it 1, 2, 3, 4, 5. And then they're going to look at that across a period of time and determine, or at least, if nothing else, look how close apart they are happening to each other, and they'll be able to figure out how fast that part is spinning. So that's a variable reluctance type speed sensor, 2 wires. So if you have 2 wires in a speed sensor, at least in a transmission, you could be pretty confident that it's just a variable reluctance type. There are also 2-wire speed sensors called magnetoresistive, and they're different, but they're mostly used in like ABS, wheel speed sensors, that kind of stuff. There's another type that's called a Hall effect, and that's what this one is. So a Hall effect type speed sensor's got 3 wires to it. It actually receives power in ground, just like a device would, and then it's going to have a signal wire. And there are 2 different types. Usually the signal wires are going to, you're going to have a voltage being applied from the computer, and the Hall element grounds it out. But there are some Hall sensors where instead of having the computer provide the power, the Hall element outputs a 5-volt or a 10-volt square wave. But this one here, it grounds out a signal. So we're going to go ahead and wire this up. We've got, mark that, plus and minus. Power is, we're going to put 12 volts to it. And I've got white as the ground. And then this is my signal wire. So the signal, it's going to be grounding out a signal that the computer provides. So the computer is going to provide 5 volts, and then this is going to, or 10 volts. The voltage that a Hall effect device works at could be different from different manufacturers. But we're going to just use our 5-volt output from our regulator. But we're going to have it go through a resistor because when it grounds out, we don't want to short out the 5-volt circuit. So I'll just use one of these. This is a 100,000 ohm resistor right here. And you can see I've got power going in. So if I provide this circuit there, now I'm going to have 5 volts through a dropping resistor going to this circuit. I'm going to go ahead and hook up my scope to it. And a Hall element works in a similar fashion in the fact that it does use a magnetic field, and as the flux lines change, we're going to get a reaction. But what makes it different, it's still got a magnet in there, but what makes it different is that the magnetic flux lines influence a Hall device, a Hall element in there, and it toggles a circuit to ground out this signal wire. So instead of getting a sine wave, you're going to get a square wave, and it's going to be DC, not AC. One of the benefits of this Hall sensor is that we can measure slow rotation. With the variable reluctance sensor, if it's going slow, the flux lines aren't changing fast enough to induce a lot of current into those wires. So we don't actually get much of a voltage change. It requires some RPM. Whereas this Hall element, if we can go slow because it'll just, you can see right there, if my voltage is high, I'm moving this really slow and you can see my square wave pattern is changing. And the faster I go, so a Hall sensor is very accurate, especially at monitoring speed. But it's going to do the same thing. It's going to count how many times it switches to figure out how fast it's spinning. You can see this does a better job than your variable reluctance sensor, but one of the reasons why it's not used all over the place is because it's more expensive. Simple as that. Now we're going to look at pressure switches and pressure sensors. This is showing that 6L80, they use pressure switches a little different than that 4L60 example that I showed earlier. The 4L60, they showed pressure switches to determine manual valve position. In this case, the 6L80 uses pressure switches to indicate whether a clutch circuit has fluid pressure in it. So you're going to see these values change, as you can see on the table there that we've got. It shows basically 4 switch circuits and whether or not they've got pressure in it or there's no pressure, exhausted. So if it's got a 1 listed there, that means it's got pressure in it. If it's got a 0, that means it's exhausted. It's really a feedback circuit. This is an input, so we're talking about everything that provides input to the computer. So the computer is going to be able to look at these 4 switch circuits to find out if the hydraulic circuits are sealing up and operating as intended. They can also see how quick the hydraulic circuits are filling up. So these switches are going to close at a predetermined pressure. I don't really know what they are offhand, but I'm going to guess about 20-25 psi. So once there's a certain amount of pressure, the switch closes and that informs the TCM of the integrity of that hydraulic circuit. I don't know if you'll be able to keep up with this, but this is that example. I've got my 4 pressure switches right here. 1, 3, 4, and 5. I'm in first gear. So high, high, and low, low. Oh, now we just switch high, high, low, high. No. Okay, we're in second gear. High, low, low, high. So it's high, low, low, high. Then we switch into third gear. We're in low, high, low, high. Hello, hello. Fourth gear. High, high, low, low. Fifth gear. Low, high, high, low. And lastly, sixth gear. 3 highs and a low. That does not match up with my chart. Now, a pressure sensor is going to be a little different. A pressure switch is just designed to be open or closed, and it's going to have a set pressure at which it closes. So it's going to be taking a voltage and pulling it to ground when that switch closes, and they're going to measure the voltage drop across of a dropping resistor. Whereas a pressure sensor is going to provide information on the actual pressure. So computers might use a pressure sensor, or manufacturers might use a pressure sensor when they really want to make sure the actual and desired match. I mean, if they desire 210 psi and they need that, they might have to have a pressure sensor in there to prove that they're getting 210 psi. And they can tweak and adjust their solenoids and their hydraulic operation to get the pressure that they need. So that's the reason why they might use a pressure sensor to ensure the electronics are controlling the hydraulics properly. An example would be on the CVT. This is a Jadco CVT, and they've got, in this case, they got on this illustration here, they got primary and a secondary pressure sensor. Well, the pressures are very important in a CVT. They want to make sure they've got adequate pressure, or else that belt can slip in there. If the belt slips, those things are going to be toast. It's 5 volts in, this is ground, and then this is going to be my sensor signal, so it's going to vary. 0.5 is 0 psi on this, and then I think 4.5 is about 1,000 psi. They can look, they've got the lookup table in there, so they know what voltage equals what pressure, and then they'll do those comparisons. Same thing with the secondary pressure sensor here. I got my 5 volts coming in, I got ground, GND, or GRD, I'll put it, and then this is my signal wire. This is different. This isn't a pressure switch like we saw first. This is a sensor, so it's going to vary its output based off of how much pressure the transmission produces. And in this case, it's used on a Jadco, and it's a primary or secondary variator pressure. So this thing's designed to read probably up to 1,000 psi or so. But it's going to receive 5 volts and ground. So it's a 3-wire device, so it receives power and ground. And then that third wire, get in there, and that third wire is just going to basically be the sensor input. So if I were to draw it up, we got 5 volts going to our variable sensor. I'm going to draw it with the box with an arrow through it because it's not really a variable resistor. And then this third wire is going to be our signal input, PSI. The computer is going to have a lookup table where they're going to be able to say what voltage is what pressure. So right now with this hooked up, there's about 1/2 volt showing. I changed the scaling on the scope to plus or minus 5 volts. And that's no pressure, 5 volts. So if I took my air pressure instead of hydraulic pressure or ATF pressure, you can see as I gas it, give it a little bit of pressure, it goes up. It goes up to about almost a volt. So whatever voltage it goes to, let's say this has got 60 psi in it or so. I don't know if this was about 0.9 volts. So there's going to be a correlation. There's going to be a table that equates a certain amount of voltage to a certain amount of pressure. So that way the transmission will know exactly what pressure we've got. And some transmissions are going to need to know that, because if they can adjust, they might need to adjust the pressure in the transmission based off of the load that the engine's putting out. And they want to know specifically if the pressure that they're trying to achieve, they're actually getting. So they might put a pressure sensor in this transmission. Not all transmissions have pressure sensors, but there are plenty of them that do. Another important sensor is a load sensor. They really need to know the torque from the engine so they can make sure that they got the transmission operating at the proper pressure so clutches don't slip. We don't want to overestimate the torque coming out of the engine, or because we can make the transmission shift harsh. We definitely don't want to underestimate the torque coming from the engine, because then we won't have enough pressure and clutches could slip and burn up and cause durability issues. So they use these load sensors, and most vehicles have a mass airflow sensor, and a mass airflow sensor is going to measure the amount of air coming in the engine. The more air you got coming in, the more fuel you're mixing with it, the more torque and power your engine's going to produce. If you don't have a mass airflow sensor, then you're going to have a speed density system, and they're going to use a MAP sensor, engine RPM, engine coolant temperature, and intake air temp. They're going to have all these things to calculate load. But still, you want to make sure all your sensors are reporting accurately so that they're reporting on the correct amount of load, so that way your transmission can operate properly. It's one of those things that this is an engine-related sensor, and a lot of people aren't thinking about that, but it could definitely cause transmission-related issues. So information on the engine torque is a big piece of the puzzle for transmission operation, because they want to match the pressure to engine load. More pressure for higher torque and lower pressure for less torque. They're also going to use that load information to maybe delay your upshifts when you're under a load, and also to control your torque converter clutch. If you're under a lot of load, they'll keep the torque converter clutch off so you can multiply torque and keep that engine RPM up. And then when you're just cruising and you're not creating much load at all on your engine, they're going to apply that torque converter clutch for fuel economy and reduce temperatures. So I got this video right here. I was brake torquing the Silverado. It was on jack stands, so I kind of had a hard time getting the brakes to hold. You could see they've got the actual torque value. They've done the calculation in there. It's not like they got a sensor measuring the torque. They're adapting that from the amount of air coming in. This is basically a volumetric efficiency, how well the engine's breathing. And then this is how they're calculating that based off of the RPM and the amount of air coming in, grams of airflow per second. They do a VE calculation on that, and they can tell how much percentage of load based off of what they know about the engine and how much torque it can produce. They can look at this percentage of load and the RPM range and figure out how much torque that engine's producing, so they can share that information with the transmission so that way it can make sure it has enough pressure to keep this thing together. This is a simple mass airflow sensor here, nothing too exciting. I've got 12 volts coming in, I got ground, and then this is a signal circuit right here. This extra wire, this third wire, they're delivering 12 volts to the mass airflow sensor through a resistor, and then the mass airflow sensor has a transistor in there and it toggles it to ground. So our mass airflow sensor on this GM creates a square wave, or digital on-off signal. And based on the frequency, how often this signal's toggling, 12 to 0, based off the frequency, that equates to how much air is coming in. So they'll measure the frequency of that sensor and figure out, based off of the frequency, how much air is coming in the engine. The power is supplied by the computer, and then the mass airflow sensor grounds it out. And this one built into it is an intake air temp sensor as well. This is a mass airflow sensor. A General Motors type mass airflow sensor is real common. We got a bunch of these just laying around. And the way it works is I've got 12 volts going to the mass airflow sensor, and I've got ground heading back. And the computer is going to provide a voltage signal. We're going to say we're just going to do 5 volts again. And through a dropping resistor, it's going to, the mass airflow sensor is going to toggle that to ground. So I got B plus, ground, and then the signal wire. And I'm going to get a frequency on that circuit based off of the airflow, the speed of the air coming through the mass airflow sensor. And I need to provide the voltage from the computer, and it provides the ground and toggles it. It sits there and switches that signal back and forth. So let's see if we can't wire this up. Okay, so I've got my GM sensor wired up, got power and ground. I got 5 volts going through a 100,000 ohm resistor, and it's switching. The sensor is doing its job switching that. It will change the frequency based on the amount of air that's flowing in. And on the scope image that you see, you actually see the frequency of it just sitting there. And that bottom line, that black line, that's actually showing the frequency. I did a math channel, and it's showing the frequency that it's measuring. You can see when I start blowing air through it, not only does the frequency change, but you'll see the black line kind of change as well, indicating that. That's how the GM mass airflow sensor operates. And the computer is going to use engine load to determine what pressures it needs to run the transmission in, how hard to shift a clutch, so that way it's not slipping too long. So load is a very important input to the transmission function. A mass airflow sensor is a very common device to measure or determine engine load. If you got more air coming in the engine, the more torque your engine is going to produce, and you're going to need to hold all that with the transmission. So that is a big input. We'll put that over here on the input side. If you don't have a mass airflow sensor, you're probably going to have a map sensor, which I don't have to show you here, but there are other sensors that we have, the brake pedal position switch or sensor. In this 6L80 example here, they've actually got a sensor, so it's not just on-off like we would think with brake lights and cruise control. It just has to be on-off. Well, they've got sensors so they can actually determine how hard you're pushing on the brake pedal, how far your brake pedal traveled, all that kind of stuff. Also, the accelerator pedal position sensor is a big one. They're going to use both of those primarily for things like torque converter clutch control. If you take your foot off the throttle or if you apply your brake, they might pull back on torque converter clutch and let it slip a little bit so that we don't get like a chuggling or harsh on and off. So the accelerator pedal position sensor is kind of redundant sensor. They've got two of them in there, and they're going to correlate to each other to make sure that they're both reading accurately. And then the computer has the ability of controlling the throttle any way they want, but this is going to be the driver input information. If you're going wide open throttle or half throttle or taking your foot off the throttle, it'll know based off of the accelerator pedal position sensor. And the same thing along with the brake pedal position sensor. If you're in a panic stop, they'll see your foot travel really fast and go to the floor, and they can monitor that stuff, and they can control things like the analog brake system and try to keep the vehicle in control. So they're very similar in operation, even though one's only got one circuit, the other's got two. But basically, they're going to have they're monitoring the voltage. This is a circuit like if I had 5 volts and 0, it's going to be what they call a potentiometer. So the typical range of a potentiometer is between 0.5 and 4.5 volts. And the computer will cross-correlate that voltage to a position, either a brake pedal position or an accelerator pedal position. And like I said, this is mainly used for torque converter clutch control to tweak the operation of the torque converter clutch. So we looked at a variety of inputs here. There are a bunch more inputs that I've got. There are things like brake switches and accelerator pedal position sensors and all that kind of stuff. But the operation of these right here kind of carry over to the operation of other sensors. I'm just trying to give you a brief introduction to hardware-wise and how they're switching voltages and what happens in the PCM to control inputs. And think of our inputs. Some of them are extremely important. Our range sensor is important because the module is going to need to know if you're in park, reverse, drive. Otherwise, it's not going to give you gears. If it thinks you're in reverse, it's never going to control multiple speeds. Or if it thinks you're in park or neutral, it won't do that either. Our speed sensors are very important. We need to know how fast these shafts are spinning. If the speed sensor fails and it doesn't know how fast like the output shaft is spinning, it'll never be able to put you in anything but either first gear or a default gear. We also have pressure sensors. Those are important feedback. If the computer is wanting to know if it's controlling the pressure in the transmission properly, it's going to look at this sensor to say, okay, do my actual and desired pressures match? If not, then it's going to have to tweak the pressure control side of things. And then we have sensors like this mass airflow sensor that provides information on load. Obviously, that's an extremely important sensor. The computer is going to use that information to determine how much pressure to apply these clutches with so they don't slip. So if this is feeding false information, we could have transmission issues. So this engine component could cause transmission failures. So those are all inputs. So the computer is going to take all that information from these inputs, and we're going to control outputs, which we haven't looked at any of those yet. Now we're at that point where we took all this information, information from the speed sensor, information from the range switch, information from pressure sensors or pressure switches, accelerator pedal position, brake switches, load sensors, all this information that we've got. The computer, the TCM or PCM, is going to use that information, and they're going to operate the solenoid so they can put this transmission in the proper gear, and they can operate solenoids to put the line pressure or the transmission pressure at a certain amount so that the clutches stay together. So either the transmission shifts smoothly at cruising, kind of light foot throttle accelerations, or the transmission shifts firmly under wide open throttle, so we can keep this thing durable and lasting. But there's other things that we need to think about when we think about the TCM. So we want to make sure we have the proper software versions and updates. A lot of these issues that we have with transmissions can be fixed with a TCM reflash or a PCM reflash. This is an example right here on a TLX Honda on the 8-speed dual clutch transmission. It says it has a bump or hard shift when coming to a stop, usually the downshift from second to first. It's intermittent and it may be difficult to duplicate. So you can imagine somebody working on that in the shop, they'd probably be pretty frustrated, have a hard time dealing with that. That's a TSB, provides this information, but you could see the way they fix this is through software. As far as module location, sometimes you'll find a TCM located in the valve body, in the transmission fluid inside the unit. Sometimes you'll see them mounted on top of the transmission. And then sometimes they'll be incorporated in the PCM, and the PCM basically means it's going to have engine controls and transmission controls. So it could be different on all different types of vehicles. One of the things, if you've got these internal TCMs that you have to be really cautious of, is contamination. They've had issues, some manufacturers, where radiator coolers break and then they mix ATF and engine coolant. And engine coolant seems to do a nasty job to the inside of a transmission. It kind of screws up a lot of the electronics. Other things that we're going to think about as far as the electronic side, as far as the computer is concerned, shift adapts and relearn. Whenever you do an overhaul, whenever you do a major replacement, change a solenoid pack, change a valve body, you're supposed to relearn the transmission, so that way it resets all these adaptive controls. The transmission is going to try to correct for and learn the nuances of a transmission. So if you've got a little extra leak or a solenoid's not passing as much fluid as it should, it over time learns to adjust for that. Now if you replace that part and you don't reset and relearn this stuff, it doesn't know that there is anything different, so it's going to operate it still with that failure in mind. And now that failure has been addressed, and you're going to end up having a hard shift or slipping gear or something like that. So those are things that you need to be aware of. Sometimes they'll have procedures, like this says clutch break-in. Just this example right here, this one's talking about the break-in procedure on this Honda. But there are other transmissions that sometimes, especially with a torque converter clutch, they might have a break-in procedure, and that'll be done through software. So you tell it that you want to initiate that, and then it goes through the sequence that it knows it needs to go through to properly break in that clutch. I'm kind of going on this list in the opposite direction, but solenoid calibrations. The 6F50 transmission that we're going to go through, there's actually a solenoid strategy and a solenoid body ID, so you actually tell the computer what kind of solenoid it has in there, because that code that's on the solenoid is going to give information on how well the solenoids flow fluid and how they react. So they've been kind of baseline tested, given a code, so that way when you enter it in, the computer kind of has a head start in adjusting for that. Already mentioned software revisions and the location of the computers. So yeah, the TCM, it's all about taking the information that we've got from these input sensors, and now it's going to control these output devices, which is what we're going to look at next. Outputs for these automatic transmissions are mainly solenoids. I mean, you could break down and say, okay, well, there's lights for the Prindle on your dashboard and the CAN bus or a diagnostic link connector, that kind of stuff. But for the most part, when we're thinking of the operation of a transmission, we're really dealing with solenoids. We're going to have solenoids that control pressures and solenoids that control the movement of shift valves. And, as we learned with the valve body discussion. These are some examples too. Nowadays we've got park lock actuators. So there's most modern transmissions don't actually have a cable shifting you in and out of park, mainly because of start-stop technology. They want to be able to engage park without you doing it. If you are sitting there and the engine's off and you open the door to get out and you didn't realize you never put it in park, well, as soon as they see the door open, they can lock you in park. So they want to be able to do that. That's why now you've got these park lock actuators on a lot of these vehicles. There's different ways they do that. But on-off shift solenoids is a pretty common in most transmissions. Like up here, we've got on this Honda, these are on-off type shift solenoids, and these are PWM or linear solenoids. Those are the ones that are going to vary pressure. They're variable output, the linear ones. And then the on-off type is just basically pass fluid or trap fluid, pass fluid or trap fluid, and they're going to shuttle valves. And the solenoid operation is getting pretty heavy. This is a Honda 10-speed. They've got 15 solenoids in that transmission. Getting more and more complex electronically every day. The valve bodies are actually getting simpler because they're replacing the valves with now solenoid and computer control. PWM solenoids, also called linear solenoids, variable electronic force motor, electronic pressure control. I probably should put PWM right there because those are all different kind of terms that people use. Basically, we're just saying that we're taking a solenoid and we're turning it on and off, pulse width modulating it, and based off of the amount of on time, the time that it's actually got current flowing through it, is going to determine how that solenoid is going to react. I mentioned down here that these solenoids could be normally passing or normally trapping. If it's a normally passing solenoid, that when it's electrically off, thus the normal part, it's going to pass fluid through it. So it's going to deliver fluid to a clutch or something like that. Whereas some solenoids are normally trapping. So if I have no power going to it, fluid cannot find its way through that solenoid. So, and it could be different. It's different on different transmissions. The first transmission we go through is the 41 TE. They've got 2 solenoids that are normally passing and 2 solenoids that are normally trapping. The reason why they do that is if the transmission ever fails and loses power, that we know we've got 2 clutches that are on and 2 clutches that aren't, and that's going to give us second gear in the transmission. So they do it on purpose for a reason. One of the other things that we note about PWM or linear solenoids, they typically will operate that at a constant frequency, and they'll change the duty cycle. So like, up here, this is maybe 50% on time, and they could operate it at like 10% on time and 90% off. But the frequency, you can see I got 4 pulses right there, I got 4 pulses right here. How frequent the pulses are happening, pretty much the same. It's just they change the amount of on time, 50% versus 10%. And by doing that, we're actually going to change how fluid can flow through that valve, and then we're going to be able to adjust pressure through those solenoids. And it's kind of pretty straightforward. Now, when comparing it to the on-off type solenoids, they have much lower resistance. Most of these pressure control solenoids will have between 1 and 3 ohms. And that's okay. I mean, you'd be like, man, 1 ohm, that's going to be, with 12 volts, you'd have 12 amps. That's too much, frowny face, right? But remember, it's pulse width modulated. So when they pulse these things, you're not going to get the full amperage to it. You might pull 1.2 amps through a solenoid when it's fully turned on. And when I say fully turned on, that might be 50% duty cycle. But so they do that. Pulse width modulation limits the amount of current that can flow through these solenoids. But that's also the reason why they have to have that low resistance, because it's only turned on for a portion of the time. They need to have a low resistance coil to deliver enough current to create a strong enough magnetic field around that solenoid to make it do what it needs to do. So looking at these solenoids, solenoid 5, 2, 4, and 3, and when those and what they operate as far as clutch wise, I can look at the pressure command that they've got here on my data PID and see if it kind of agrees with it, and might help me diagnose it a little bit. Now this actually says the pressure. That doesn't mean they have a pressure sensor in there. That's just kind of the commanded pressure that they're hoping that clutch receives. Basically, they correlate the duty cycle of that solenoid to a pressure. But remember, this is an output. It's not an input, so I can't measure it. It's just that's kind of commanding it. So even though we see 110 psi, they're hoping that it's there, but it could in reality only have 20 psi, and there's really no way of them knowing. The only information they've got input-wise on whether or not these things have any pressure are those pressure switches that we looked at on the input side of things. But those things close at a lower pressure. They don't close at high pressure. And they're not sensors, so they don't tell what the pressure is. They just show whether or not there was pressure there and it achieved their minimum amount. So let's look at this video and see if we can kind of follow along. So right now we could see I'm in first gear, and my solenoid 3 and 5 have pressure. 5 is used in first, 3 is used in first. And now I just shift in the second. Solenoid 4 and 5 should be receiving pressure, and they are. I just shift in the third. Solenoid 2 and 5. So third, solenoid 2 and 5. This is going quick. And so shift in the fourth, I got 3 and 5. So solenoid 3 and 5. Look at that, I just got through all my, and then now I'm in fifth. Okay, so, six gears, going too fast. Third and fourth. So solenoid 3 and 4. Looking at the scan data and so forth, we can confirm whether or not we have an issue or not. If we're having an issue going into fourth gear or third gear or sixth gear or whatever, we can see if the command was made. We could see if the gear command was made. We could look at the RPMs to see if they changed. So anyway, it's kind of example that I was just going to throw out there and give you, because we're looking at these PWM solenoids. So when these PWM solenoids are working, like in this example here, solenoids to, this is going to operate second and sixth gear, that it's going to pulse width modulate to deliver the fluid pressure into the circuit in a fashion that the clutch is going to apply smooth like they want it to. When we look at outputs on automatic transmissions, we're basically dealing with solenoids. We use all this input information so that the computer can decide how to control some solenoids. And I've got a couple solenoids here as an example. This is a solenoid out of a Mercedes, and it's a pulse width modulated solenoid. So fluid is actually going to enter in through the bottom, and based off of how this solenoid is operating, it's going to come out and operate a clutch circuit. And I put a pressure gauge on here, and we're going to try to control this. It's not the easiest thing to do without more advanced circuitry. I got two of these MOSFET transistors. The way that most solenoids are wired is I'm going to have 12 volts going in through the solenoid, and then it's going to come into the computer, and the computer is going to control the ground through a transistor. And the transistor is going to, when they apply voltage to the base of that transistor, they provide ground. If I hook up to the gate of the MOSFET, if I control that, I'll actually turn the solenoid on. I've got this little box that I made years ago, and I can actually output a digital 5-volt square wave. And so I'll hook this thing up to kind of mimic what a computer is going to do. It's going to try to pulse that solenoid. And I'll have power. I should probably have something protecting that, but I don't. And then I'm going to have ground hooked up to this guy. And then when I turn this on, you can hear it operates that solenoid. They'll operate these things at a fairly high frequency, so you wouldn't normally hear that. I went ahead and put the scope on there, so I've got the scope grounded out, and it's connected into the ground side of the transistor. So I'm checking the voltage right here so we can see how it's controlling the solenoid. So when the transistor is applied and it provides a ground, I drop all my voltage across it, and I see the voltage drop low. And when the voltage goes high, the transistor opened up the circuit, and voltage went up. And then when the transistor provides the ground, it goes back down, and I get the square wave. The amount of time that they keep the pulse on is going to determine the position of the valve inside the solenoid, and it's going to ultimately control how much fluid pressure finds its way into the clutch circuit. So like right now with it off, you can see nothing gets trapped in there. You look at that gauge. When there's no electrical current flowing through it, it lets everything leak out. Now you can see on the scope image there, I'm controlling the frequency and the duty cycle. So you can see how controlling the pulsing of the solenoid can control how much fluid flows through it. This isn't the best example because what they normally do in a computer control solenoid is they operate the solenoid at a constant frequency, let's say 300 hertz, and then they vary the duty cycle, how much on time it is. This little box right there, it doesn't really change the duty cycle, it just changes the frequency. So I'm not getting the exact same effect, but rest assured, if you're doing this and the computer's in control of it, it changes the duty cycle, the amount of on time to control the solenoid. So with this thing electrically off, it passes pretty much everything through it. It doesn't trap any pressure in there. And then they energize it. The more they energize it, the more hydraulic fluid gets passed through, so into the hydraulic circuit. That's just one way they control it. So this right here is an output, and it's a variable output. They change the output of this solenoid to change the amount of pressure that it finds through it. One of the outputs that we've got, it's called a PWM or a linear type solenoid. With these on-off solenoids, things are a little simpler. Looking at this electrical schematic, it really doesn't look any different. We've got like a pressure PWM, a pressure control solenoid, and it still provides a ground. Now they're going to pulse this though, like we talked about. You're going to have on-off, on-off. It's going to be a fairly high frequency. It's probably over 500 hertz, a little bit over 500 hertz. But some of these other solenoids are basically just on-off. So they just have they do have a transistor in there, but they're not going to pulse it. They're just going to provide a ground, and then they're going to open it up. And they can do diagnostics on these circuits to see. Typically your output circuits like this, they're limited on what they can check, but they do put a voltmeter on at the circuits right here, just before the transistor that grounds it out. They look at the voltage on that, and they just make sure that things are reading properly. Because let's say, for example, right now with these solenoids open, they should all be seeing 12 volts. And then when this transistor closes and it provides the ground, all that voltage is going to get dropped across this solenoid, so they should see 0 volts. So if they ever see 0 volts when the solenoid's supposed to be off, they know there's a problem. It's either an open circuit somewhere or a short to ground. And if they ever see 12 volts on this, when it's supposed to be closed, they know that there's either a short to power, it's supposed to be a B plus, not 13, or this driver's bad in the computer. So they can do diagnostics, and they'll set codes based off of that. And sometimes they'll actually see where they measure current flow through, especially these pulse width modulated solenoids. Sometimes they'll monitor current flow through it. When they monitor current flow, you can see an actual and desired amperage right there on the scan tool, and that's beneficial. Usually when you see that though, you don't have just 12 volts feeding a bunch of solenoids. You'll actually have a dedicated power and ground for each solenoid, because they'll do a comparison in there to calculate the current flow. So usually when you see a bunch of solenoids banked together off the same power feed, like you are in the 6L80, where they're all kind of tied into the same power feed, they're not going to be monitoring current flow through it, but they still can do that voltage check there, right there at the just before the transistor. This is another output that we've got. It's a on-off type solenoid. They're a little different than the PWM or linear type solenoids. As the name implies, on-off just means they turn it on or turn it off. These linear type or PWM solenoids, they're low resistance. They only have maybe 1 to 3 ohms of resistance, so they can pass a lot of current. They need a low resistance circuit so they can build up a strong magnetic field quick. Whereas most on-off type solenoids, they're usually higher resistance, maybe 20 to 40 ohms, so they only pass about a half of an amp. And it's going to be wired up pretty much the same way. I've got 12 volts coming in, and it's going to go through my coil, my solenoid, and then it's going to go to a transistor to ground, and the computer is just going to control power to the base of that transistor. It's simple as that. Now, so really when I go to operate this thing and wire it up, I've got this MOSFET in here, so it's a little different. I've got power coming into my solenoid, and then it's coming out and it's going into the drain of my MOSFET. The drain's going to be able to transfer it to the supply, and the supply is going to end up grounding it out. The gate of my MOSFET is this yellow wire right here. So when I energize it, hook it up to 5 volts or so, it's going to allow this solenoid to turn on. So you can see when I ground this circuit out, voltage drops to 0. When I open it up, it bounces back up to 12. Normally you'll see an inductive kick with the solenoid. I don't know why we're not seeing on this. It's probably the way I have it wired up. But either way, it'll still work for how we need it to work. Now the way that this ends up operating in the transmission is fluid comes in through this hole, and it's going to leak out through the snout that we've got. And also all that fluid pressure is going to come out when the solenoid's off right through the snout. Then when we energize the solenoid, it pushes a check ball and seals it off. And then pressure builds up on the back side and it shuttles this valve. When I provide power to that transistor and energize the solenoid. So that's basically how an on-off solenoid operates. Realize that your transmission might have 5 or 6 solenoids. Some of them might be pulse width modulated, some of them might be on-off. But it's going to use all this information from the input side, make a decision, and control these output solenoids so you get the gears and the pressure in the transmission that you need. So that's kind of a different way to explain the electronics and demonstrate it. Hopefully it made a little bit of sense. I know this can get a little crazy and confusing, but hopefully it worked out.